Okay, I think we will go ahead and get started. Um, so just a couple announcements. Um, Friday, hopefully, seeing how this person will only be traveling from Mount Sinai, so it's just going to be coming from up there. We do have another speaker. It's not an organic chemistry talk. It's actually not even a chemistry talk. It's going to be more of the lines of biology, but it's going to be Dr. Megan Shaw of Mount Sinai. She's a sort of microbiologist, neurologist who focuses on influenza. She's going to talk about sort of developing new drugs, for example, for influenza. So it should be an interesting talk. Again, this is sort of more a person I'm inviting here because forging relationships with the biology community to sort of benefit my own research. And so she's younger, in the area, and does some really nice work. And so if you want to come, it's going to be at 2:30 in 432 New Ingersoll. Second announcement, get your corrections to me, get your exams. I think today was the deadline to get any regrade request forms, or shoot me an email to let me know why you can't do it by today. I have had a few people who emailed me, so definitely check your scores. That's something, just check it. If there's a mistake on adding or something, let me know. In particular, what both adding mistakes have been, because we always double check the addition, but what we don't necessarily double check is, say, for example, if there's a question that's 2 parts, every once in a while you can imagine as you're grading 220 exams that you have the 2 and you accidentally just grab one of them instead of adding them. So double check to make sure your grades are graded appropriately, because we've had 2 that have been like that. So just check and let us know. That's obviously an easy fix. Third announcement, well, I guess I have quite a few announcements. Third announcement, quiz is going to be basically next week, except we don't have class next Friday, so if you're in Friday, it's going to be this Friday. The topic, again, is always whatever you've had a weekend to prepare for. So the people that have it at this upcoming Friday, it's going to be focus on amines, so know the chemistry of the amines. If you're the following week, then this chemistry that we talk about this week will also be fair game. We will start to revisit synthesis problems. So again, as you know, as you might imagine, I could certainly ask questions. At this point, it might be a good time for me to ask questions related to, say, for example, aromatic chemistry, where regioselectivity might be involved. So now would be a really good time to make sure that you're up to speed on synthesis and the regioselectivity of aromatic compounds. So again, the focus will be on likely amines, and for the following week, probably cross-coupling reactions. But again, it's probably a good time to quiz you guys on synthesis as well, and so be prepared. I'm not saying that you will, but now would be a good time for me to ask a few aromatic synthesis questions. The final announcement is sort of where we are in the course right now, and just sort of a reminder and just sort of a heads up. So we're at the end of this week. I plan to be pretty much done with sort of organic chemistry per se, and what I mean by that is sort of within the realm of synthesis. So we're going to discuss cross-coupling chemistry, and again, we'll be discussing chemistry a little bit more in depth as we move further down, but it's going to be more related to sort of application, and specifically things like polymer chemistry. So we'll talk about polymerization processes, but those won't necessarily be sort of small molecule organic synthesis that we focused on to date. The other thing we'll start focusing on is things like peptide couplings, which we've certainly seen how to make amides, for example, but we'll discuss methods for the synthesis of peptides. We'll discuss things like nucleic acids and sort of start to get into a little bit more of the biochemistry side of things. I should point out that my sort of personal feeling about a lot of this stuff. So I think that synthetic chemistry, organic synthesis, learning and reactions synthesis I view more from the standpoint of problem-based learning. I think it's a standpoint where you have to learn a lot of information and then apply it in complex settings, which is, I think, a good challenge in terms of puzzle solving and problem solving and work ethic and those types of things. The part of the course that we're going to get to, and this is just so you guys are understand where I'm coming from, I view as much more culturing, right? We're going to start to make that transition. So I don't view, this is kind of perhaps a celebration in a way, because I think the most intense part of the course is coming to an end, right? Organic reactions, mechanisms, syntheses are largely coming to an end. And when we start the new stuff, it's not to say that it's not going to be challenging and so forth, but I hope to, as I teach it, I hope to more sort of culture you guys, give you guys some introductory to applications of synthetic chemistry, and I'm going to be less concerned about, I think, sort I'm looking for, driving you guys crazy, trying to like really get you guys working hard to get synthesis and stuff. I think it's just going to be an easier topic of the course. So I don't plan on making super challenging problems, for example, at that point. It's just going to be sort of culturing you guys and getting you guys ready for whatever courses you may take next within the realm of chemistry. Okay, so that's just so you know what is ahead. And so this week, what we're going to be focusing on is metal-catalyzed cross-coupling reactions, or coupling reactions. So we've discussed a little bit before already. We've seen in the past, if we start thinking about organometallic again, we've seen throughout the last couple, throughout the last few semesters of this course, we've seen quite a variety, I think, of organometallic reactions to date, right? So without perhaps even really recognizing, perhaps it's been brought up in the context of something else, but certainly organometallic species, and what I mean by that is carbon, metal, hybrids, if you will, have certainly been important to us, right? And so we've seen instances in the past, right, where if you take an alkyl halide, for example, and you treat that with, say, for example, magnesium. We haven't really talked about this mechanism that much, but obviously in case these two react together, you guys know at this point what you form is a Grignard, right? We discussed this more within the realm of carbonyl chemistry. And we think about this molecule as being at least from the reactivity standpoint, what happens is the magnesium actually inserts into that alkyl that alkyl halide bond, right, whether it's a bromide or a chloride or an iodide. We'll discuss this a little bit more in terms of oxidation. Basically what happens is the magnesium goes from what we call an oxidation state of 0. We're not going to be talking too much about this sort of electron count, but when it inserts into that alkyl halogen bond, what happens is then it's kind of, you think about it as giving up a couple electrons to make these two bonds, taking the metal to an oxidation state of what we consider 2. This is perhaps one way that you could draw this molecule. How I generally like to think about it is like this, right? That we have a alkyl nucleophile, right? And then we have this sort of counterion. But again, the mechanism of this process, while still, I think, not completely understood, there's ideas that it could be sort of a radical single electron process. But formally, you can sort of think about it as this process, right? The magnesium is inserting into these bonds. Again, we've seen other examples in the past. Now, in the case of a Grignard, it certainly, I think, from a reactivity standpoint, behaves and reacts much more as this dissociative bond. I often will say you can just sort of forget, after you've made the Grignard, you can forget about the counterion and just sort of draw arrows as if the alkyl is a nucleophile. However, we've also seen chemistry And so again, if you take a Grignard, right, in particular where we've seen Grignards react, for example, right, as ketones, right, where we add in, and after an aqueous workup, right, we can get things like alcohols. And as it turns out, you can definitely consider Grignards nucleophiles for a variety of other reactions, but certainly they can behave as bases. So if you try to take, say, for example, Grignard and treat it with, say, for example, another alkyl halide, this can work. You can certainly get coupling, right? So you can imagine if you did this, you can certainly get coupling chemistry. But as you sort of might also know, Grignards can also behave as bases, and so you often get things such as side reactions where you'll get sort of elimination, right? So you can also get elimination in these cases. But the point that I'm trying to make here is that in the case of a Grignard, at least in principle, you can begin to get substitution chemistry. Now, in order for you to take a nucleophile, right, and treat it with an electrophile, we need an sp3 hybridized carbon, right? And we've seen this in the past. Right? Because if you take the same molecule, right, and you treat it with, say, for example, vinyl iodide or something like that, the reaction won't work, right? Perhaps you can get Ward's coupling for radical-based process, but at least in terms of this type of substitution reaction, you will not be able to do this type of substitution reaction. Thus, we learned this subsequent organometallic reagent, right, where if we take these molecules and you treat it with something like butyllithium or lithium-0, I think the book uses lithium-0, right? You're going to do what? You're going to make the alkyl lithium species, I guess using two equivalents, because you would also generate lithium bromide. And then you're going to treat that with a copper source, right? Something like copper iodide, right? In these cases, what's going to happen is you are going to generate the Gilman reagent, right? Which we'll often call QE, right? Now, in this case, we've learned that with Gilman reagents, you in fact can react these with things like vinyl iodides, right? Now they can actually displace these molecules, right? And what you can begin to get is substitution chemistry on sp2, right? So this is one of the areas where we've initially been exposed to organometallic reactions. So again, making carbon metal species, in all of these cases we can think of them as sort of nucleophiles, right, because they're donating electrons to make new bonds. In the case of the Grignard, we see what some of the problems are. Certainly in the case of a Gilman reagent, we won't get as much elimination. So there's advantages to making, say, something, for example, like this. Okay. Now, one of the problems with a Gilman, right, is that when you make this molecule, right, you notice that you're going to have two equivalents of that alpha group, right? So you're effectively having a sacrificial alkyl group. Okay, so now imagine you're in a situation where, and that's fine, say, for example, if it's a methyl group or something that's really cheap, right, that you can get very readily. But if it's a situation where, say, for example, that R is very precious, right? Say, for example, it's really expensive, or say, for example, it took you a lot of time to make, right? You're not going to want to take a hit, right? The best possible scenario would be that you're going to get only 50% yield based upon this R group, right? Because the other one's sort of going away. However, and we wouldn't want that. So even in a best case scenario, you'd only get, say, for example, 50% yield. So the Gilman reaction is certainly good. It's useful. It's one of these ones that we sort of show. But you can understand that depending upon how precious this alkyl group is, you may not necessarily want to give up that equivalent. Furthermore, The sort of chemistry involved here, you can imagine, could also be difficult as well. You got to make an alkyl lithium. These could sometimes be pyrophoric, the reaction, and it would react with moisture, so it might not be the easiest reaction to run in a sort of aqueous environment. And so as we transition to this sort of new chapter, we're going to start to talk about palladium-catalyzed cross-coupling reaction, which, from a practicality paper chemistry standpoint, might not necessarily seem like that big of an advantage over something like a Gilman reaction. We'll sort of see it does a lot of the same things the Gilman reaction does. Hopefully you'll be able to appreciate, as we're sort of discussing these, that a lot of these sort of limitations can certainly be overcome, particularly as it relates to this sort of alkyl group and the ways that these are synthesized. Okay. Now the other thing, so I'm going to sort of introduce these, and one of the things that I sort of want to point out is when we react a nucleophile with something like an sp3, basically standard substitution chemistry, and I'll get back to this in a second, but I think one of the things that's sort of glossed over early on with these Gilman reagents is actually the mechanism through which these work. It's not necessarily your standard substitution reaction, right? We've learned that substitution can only take place on sp3 electrophiles like we saw, but Gilman is perhaps a little bit different in that regard. So within the realm of organometallic reactions, we'll get back to the mechanism in a moment, but what we're going to introduce here is a reaction that we'll call palladium-catalyzed cross-coupling reactions, right? And just as a reference, I'll just put down the Gilman again really quickly, just so we can refer to it. I should have just left it up there, but again, you can remember previously what's happening is you've got this Gilman reagent, and you can react it with R1, R2. And you can react it with halogens, and this will very cleanly make carbon-carbon bonds of a wide variety. Again, this is why it's sort of valuable, constructing carbon-carbon bonds. Okay. In a palladium-catalyzed cross-coupling reaction, we're going to see very similar components here. And so we'll think about this in many ways, even though it's not necessarily your standard substitution reaction, we still will sometimes classify these as a nucleophile and electrophile. Even though those definitions don't necessarily relate to what we think about mechanistically with substitution, they're still sort of classified in this way. And in many ways, again, it's just the terminology, for example, that metallic chemists will often use to describe the two components in a reaction. And so when we talk about palladium-catalyzed cross-coupling, what we're going to talk about is specific metals, and so I'll just abbreviate the metals as M and discuss what those can be in a moment. But you've got some type of a carbon-metal bond. Again, you only need one, unlike the case of the Gilman, right? Plus some type of alkyl halide, okay? And it turns out, in general, when you mix what we'll discuss in terms of types of metals here, they won't react. But if you add a catalytic amount of palladium 0 to this reaction, sometimes palladium 2, or other metals, but for the focus of this course, what we'll talk about is just palladium because it's the one that's been used widely. And again, when I'm saying catalytic, what I mean is sub-stoichiometric amounts. So what I mean is you would only need, in principle, one molecule of this to do thousands of reactions of this, right? It will just be doing it over and over and over again, driving the process. And again, then what's going to end up happening is you're going to get that carbon-carbon bond. Okay? So from a practicality standpoint, you can imagine that if you could generate some type of alkyl metal bond, right? Rather than this Gilman reagent, right? We can sort of save on the equivalents that we would need, treat it with effectively the same type of alkyl halide that would be used as a Gilman. And in this case, what we're going to do is get a carbon-carbon bond. Okay, so this is an extremely powerful reaction, yeah. Exactly. I think that's one of the big advantages to it, is certainly that case. And we'll talk about, as we'll discuss, the metals. Right now we'll discuss some of the different metals that can be employed. These metals sometimes are much easier to synthesize. You can make them, say, for example, and store them, whereas something like a Gilman reagent isn't necessarily going to store for that long. So you can buy lots of these. You can make some and keep them around for months at a time, go back and use them later on, whereas something like Gilman, you might have to be a lot more careful about. And again, I'm saying that more broadly, and as we'll discuss, depending upon what that metal is, that can be sort of true or not. Okay, so the two most popular metals that we see in this type of chemistry, and certainly I would say the two that are the most widely used, are boron specifically boronic acid. So if you can make a boronic acid of this type, this can serve as your metal. In terms of the activated source of this, anytime you run a reaction, well, not anytime, sometimes people have made boron derivatives that don't require this, but in general, when you run the reaction of this type, where your metal is the boron, you usually need some type of aqueous environment, because as it turns out, this is not the active form. As you can imagine, that's electronically poor in nature, and so when people run these reactions, they do them in usually water, and usually some type of base. Again, these bases can vary. Sometimes it's sodium hydroxide, sometimes it's potassium carbonate. The idea here in this reaction is that your nucleophile is actually the borate. And so the active form and the active sort of metal in this process is the sort of borate. And so this is the active form. This reaction right here is called a Suzuki. Well, this is not this reaction, but the cross-coupling reaction employing boronic acids is called a Suzuki reaction. Okay. This is, for various reasons, is the one that people generally like to use when they can. Boron, you guys know how to make carbon-boron bonds, right? How do you guys make carbon-boron bonds? BH3, right? So you can basically add boron across, say, for example, an alkene, right? As it turns out, you can also trap. There's sort of electrophilic sources of boron, right? So just to sort of discuss this really quickly, we can synthesize boronic esters very readily. You wouldn't necessarily want to use BH3, right, because we wouldn't get to this, right? But there are things that we can add across there, say, for example, hydration using, say, for example, boron pentaclase, right? So you can sort of certainly add these across there. Sometimes these are catalyzed in principle by rhodium, but again, just from the standpoint of hydration, and now you get your alkenoboronic ester here. Okay, now in this case, right, you could imagine that if you ran this, these can also be used in the Suzuki, and they're fairly commonly used. But the hydrolysis process, right, you'll eventually get to this if you simply treat this with water and base, right? So this is again going to be the active sort of component in this reaction. Okay. Other ways that you can make these. When I did Suzuki couplings in graduate school, the way that I went about it is you have, say, for example, an alkyl halide. You can take these molecules, in much the same way as a Gilman reagent, you can first treat them with some type of alkyl lithium source, right, to do lithium halogen exchange, or as you guys have learned, so just to say standard of what you guys have learned, I'll just say lithium 0, with the point here being that you would generate the alkyl lithium species. And then there are electrophilic sources of boronic esters. And so you can buy this, say for example, where X is a chloride. The one that I did actually was X is an isopropoxy group. It adds in and the isopropoxy kicks off rather than one of these groups. So this is another way that you can generate boron chemicalates. And again, these will work. And so when I did this reaction and I did coupling, I made it effectively through this. I used a transmetallation reaction. And again, and there's some other ways as well, but I think from the standpoint of what you guys would perhaps know best, these are probably two of the examples that I think you guys could probably use to make these, right? This is sort of logical. If you have an alkyl, if you have an alkene, you guys can do hydroboration to get access to these. If you have an alkyl halide, you can basically convert it to the nucleophile and treat it with an electrophilic source of this boronate. Okay? And so again, this is a reaction called the Suzuki reaction. The boron, right, serves as the metal. So again, just to sort of complete the thought here, I'll just say OR2, right, recognizing that there's a variety of different groups that you can have there. You can treat that with, say, for example, an alkyl halide. I'll just put the bromide there. And if you treat this with palladium-0, what's going to happen is bonds are going to form. And then like that. Carbon-carbon bond. Okay? So Suzuki, that's usually the one that people like to do if they can do it. Now, in organic chemistry, and when you're sort of doing the reactions, specifically because what a Suzuki will require, right, is some type of an aqueous solution. Usually it's THF water, so it's not just, as you might imagine, right, organic molecules in water, probably not going to dissolve, right? So usually people use like THF water mixtures to help them dissolve. But the point is that if you run this reaction, you're going to have a lot of water in there. That's fine and great if your reaction is stable to water, but sometimes your reaction might not necessarily be that stable to water. And this is something that actually we were up against in our group a little bit. Mike Durasmo was trying to do some cross-coupling reactions, and he had an alpha-beta unsaturated ester, and every time he would run the reaction, the water would add 1,4 into this, right? So that's just one example of where sometimes Suzuki's will not work. And so when a Suzuki doesn't work, generally then the next step that people will go is something called a Stille cross-coupling. A Stille cross-coupling, the source of metal that you use is actually tin. Okay, and there's different types of tin species that you can use. There's trialkyl tin, sometimes tributyl tin. Mark Bisco at City College has actually been working with a lot of alternative tin species, which also work pretty well, but for the sake of this course, we'll just say SNR3. Now, the challenge here, right, is depending upon what these R groups are, now you've got 3 R groups around that tin, right, and some will move faster than others. And so in general, when you're doing things with tin, you got to sort of know that sp2 works faster than sp3. So usually your R groups over here will be things like methyl and butyl. So you usually use like trimethyltin or tributyltin something. And usually what happens on the other side is you have some type of sp2 carbon, like an alkene or something like that. And if this is the case, you can actually get selectivity for this carbon-tin bond being your nucleophile. Okay? So if we make that R1 and these R2. But certainly, as you could imagine, there are instances, and in fact, again, to go back to chemistry in our lab, Danielle, who's not here, was doing a trimethyl tin, and she was getting some product that she was seeing where the methyl was incorporating rather than the group that she wanted to be incorporating. So there's other issues associated with the tin as well. But again, this is usually the safest method for cross-coupling is to use tin. You have some of these other issues, but generally it's fine. You don't have to preform or anything. It's organic soluble. Generally running these reactions in sort of standard organic solvents like PHF. What do you run yours in? Like toluene, right? So is that what you said, toluene? Yeah, it's toluene. So you don't need the water for the tin, and that can have its advantages, as you can imagine, depending upon whether your molecule was soluble in these or not. And again, and then if you take this molecule, you can treat it with, I guess in this case, R3 halogen. And again, what you can get is that catalytic coupling reaction. There's a lot of others. I don't know what the book exactly discusses, but Suzuki and Stille are certainly the two most commonly used ones. There are some others. I often forget the names of them, but you can, in fact, do cross-couplings with, say, for example, Grignards. Why would you necessarily want to do that? Well, sometimes it could be valuable. It's a little bit more reactive. Sometimes you can get chemistry to work with these. So sometimes magnesium, so sometimes Grignards. Sometimes you can do zinc. Sometimes alkyl zincs will work with these. Sometimes those are the two big ones. So Nagishi and Kumada. Yeah, so these are the two other big ones that people sometimes use. So you may see these on occasion, deploying cross-coupling chemistry. But it's really these two that I think I would worry about if I were you guys. Okay. Now back to the tin. How do we make these? I think from a synthesis standpoint, in Suzuki we've seen boron in the past. What we haven't seen in the past is sort of tin and how we synthesize tin molecules. And so from a practicality standpoint, I think, Suzuki, it's inherently, we like to go to, there's another issue with tin. You guys might know tin is, especially alkyl tins, they can be rather toxic. They can lead to hair loss, right? So I blame my hair loss when I was an undergrad working with tin. So people for those reasons, people like to avoid these. But again, they work pretty well when you can. In this case, almost you always go through, there are hydrostanellations, but they're not as well developed. So in general, the analogy is something like this one here, where you take an alkyl halide, you treat it with like an alkyl lithium or something like that, and then you generally take this and you treat it with like some type of alkyl, like say for example trimethyl tin chloride or something like that. So you make the alkyl lithium, you treat it with the species, you get this molecule. Now, if your stuff is, say, for example, base sensitive and you don't necessarily want to make an alkyl lithium species, there are also other reagents that you can sometimes do. So you can actually do a cross-coupling to make the tins, which is kind of weird. So if you take your alkyl halide, you can imagine dimeric tins, right? So where you have tin-tin bonds, and then a palladium catalyst. Those will also generate the same thing. So again, that could be kind of palladium might be expensive. This might be sort of wasteful, what we call sometimes atom economy, because you're losing a bunch of heavy mass tin molecule. But sometimes this works well. Again, you can imagine if you're in a situation where making an alkyl lithium, that synthesis of that basic component, maybe your molecule can survive that. So this is another advantage to tin, is that you can do chemistry such as the one that I've shown you here to put them on. Okay? So again, I would just focus on these two classes. There's some others, yeah?
For the nuclear reactions, do we also have to do it in a basic environment?
Yes. What do you, which step do you mean?
The last one.
Oh, yeah. So water and some base, yeah. So if you have the boronic, just remember that you have to get to the boronate, and this is the active nucleophile. Okay. Okay. So what am I talking about in terms of nucleophile? So we know that these are, we treat these as the metals, right? So the next question becomes, well, how do these work? And from a standpoint of a mechanism, we haven't really discussed organometallic mechanisms that much. This is a really important transition metal-based process. And so you're going to be responsible for knowing this mechanism. And it's kind of your introduction in a way. It's fairly simple, straightforward. I think people generally tend to see it, get it, even if they don't fully comprehend what it means. You can become familiar with this mechanism, and then we'll see some of the derivatives and derivations from this mechanism will lead to other products. And so again, as I pointed out, the reaction is catalytic in palladium. So what I'm going to put here is a catalytic cycle. So this is a mechanism that, generally when we see mechanisms, I'm just all over the board, right? In this case, what we're going to see is that it's in fact a catalytic cycle. So I'm going to draw it in a circle to sort of show that the palladium is regenerated, okay? The general mechanism starts with the palladium, right? This is what's going to catalyze the process. And much like, say, for example, magnesium, right? We saw in Grignard, magnesium kind of inserts right into the alkyl halide bond. The same sort of thing happens with palladium-0. Okay, so if you have, say, for example, an alkyl bromide, the first step is going to be the palladium is going to insert into this alkyl halide bond. And what you'll see is that oxidation state, which is here is 0, right, it's now going to be sharing those electrons. And so it's going to go to, in essence, what we call palladium-2. Okay, and so we usually will write it in Roman numerals, just because it's fancy, I guess. Okay, so this is the first step. Now, this has a name to it. It can sometimes be useful. Okay. What type of process is this at palladium? This is redox chemistry, so is it an oxidation or a reduction at palladium? Oxidation, right? Why? Oil rig, right? Oxidation is loss of electrons. Right, so the palladium is losing 2 electrons, so this is oxidative, and it's inserting. And so the name is actually an oxidative insertion. That's what we call this. Okay, so that's going to be the first step. And that's going to be the first step in a lot of palladium-catalyzed processes that we're going to see. Oxidative insertion into that alkyl halide bond. Once we're at this sort of higher energy oxidation state of palladium, now the nucleophile can actually begin to work on this. And again, how you rationalize this mentally from a mechanism standpoint, we just call it a transmetallation in organic chemistry labs. If you want, you can think about it as, okay, now we've got this really good electrophile, so now these not so good nucleophiles can sort of add into it. But the net result is that when you treat this with that alkyl metal, so that's where the M is the metal, what happens is the R1, the R2, much like we saw in the past, say for example with just standard substitution chemistry, the R group is now actually going to displace the bromide. So how you rationalize that, if you think about it as drawing electrons to kick off the bromide, we call it a transmetallation. Okay? So again, you can maybe imagine it. You don't necessarily have to draw arrows here, but if you want to draw arrows, you can think about it as standard nucleophile. You can think about the, for example, higher energy palladium source being new electrophile. which this can add into, kicking off the halogen, generating a new metal halogen bond. Okay? The final step in this process is sort of the regeneration of palladium-2 while we also form that alkyl-alkyl bind. And so in the same way that we inserted here, this is effectively just the reverse of that. Okay, so depending upon how you want to draw it, right, we can think about it as and again, this is an organometallic course, but there are some issues associated with this. You can imagine it going through a transformation where you make the carbon-carbon bond, maybe 2 of those electrons are used to make the bond, and the other 2 go back into the palladium species. Okay. So what's going to happen here is we're going to, here's the mechanism. You want to sort of think about it that way. Okay? So what's going to happen here is you're going to make the bond, the electrons are going to go back into the palladium, and then what you're going to do is regenerate palladium-0, which can continue through the process, right? And so this is how it's catalytic. The palladium, oh, sorry, one other thing. This we call transmetallation. Okay, so that's the second step. This reaction here kind of has an opposite name to oxidative insertion. Okay, it's reductive in nature, right? Because now the palladium is it's gaining electrons, so it's a reductive reaction. And instead of inserting, I don't really understand why it would be called this per se, but it's called a reductive elimination. So I guess you're going from one molecule to 2, similar to an elimination, for example. But this is the name of this final step. Okay? And so if this is the mechanism, right, the sort of source of metal that you have here, if it's tin, then it's just the tin that's the nucleophile. If it's the boron, then it's the boronic, it's that sort of boronate, it's that negatively charged boron that would serve as the transmetallating partner here, okay? So this is the general mechanism that we consider within a palladium-catalyzed coupling reaction. Okay, any questions about this mechanism? So again, know it, be able to draw it. Okay, so again, there's basically one reaction, 2 names, depending upon the metal that you use. Again, hopefully you can recognize the 2 relative relationship between tin and boron, how some can be useful in some cases, how others can be useful in other cases. And we're going to learn a couple other reactions that, at least in principle, can employ this mechanism. So the next reaction we're going to learn is going to be a Heck reaction. It's another palladium-catalyzed process. It's going to be slightly different, so I'll put the reaction up there, and then we'll discuss the mechanism to it, and we'll try to draw parallels, right, to the palladium-catalyzed cross-coupling reaction, or at least the Suzuki and Stille cross-coupling reaction. So in the case of a Heck reaction, and I should point out that this is actually a reaction that was discovered before these. So the Heck reaction is a reaction whereby our metal, in a way, or our nucleophile, if you will, is actually the alkene. Okay? So this now is going to serve as our nucleophile in a Heck reaction. Oh, excuse me. Oh my goodness. All right. Bring it here. All right. Or just where's the chalk? So what's going to happen in a Heck reaction, it's going to be the same thing in principle. We'll discuss the mechanism is very similar. But what's going to happen here is the product, in this case, is going to be a coupling of the R2 to the alkene. Okay, and again, we're going to catalyze this with palladium. And as it turns out, there's usually, as you can sort of see, how you want to rationalize this. I'll sort of give you a couple ways that you can remember this. What's the product? If these two are reacting, what's sort of left over? HX. What is HX likely going to be? Yeah, and so if you're running a reaction, you're making alkenes, and you're generating a whole bunch of HX in this reaction, what do you think is going to happen? Yeah, it's probably going to protonate across the bond, right? So, again, as we'll see, there's mechanistic implications of this that are a little bit more complex than that. But in terms of rationalizing this, what might you want to add to this reaction? A base, right? And you don't want that base to be a nucleophile, so you want a big, bulky base. Usually it's Unix-based isopropyl ethylamine, which is simply called Dipia. Have you guys seen Dipia before? The Dipia is like one of the more common bulky amine bases, so it's kind of like triethylamine, except that instead of triethylamine, it's got a couple isopropyls, so just a little bit bulkier. So it's di-isopropyl ethylamine. So this is one of the go-to bases, and it's a little bit bulkier. So usually, this is what's employed in a Heck reaction. Okay? From a mechanistic standpoint, we're going to see there's going to be some similarities here. Okay, so that's Dipia. But again, usually you can use other amine bases as well. From a mechanistic standpoint, again, it's going to be catalytic and palladium again, so we're going to go through a very similar catalytic cycle. Okay, and we're going to start with that same oxidative insertion step. Okay, so the very first step is going to be the same. We have an alkyl halide. The alkyl halide is going to, or the palladium, excuse me, is going to insert like before. Okay. But now in this case, right now we have a new nucleophile, right? And our new nucleophile, right, is the alkene. So how you want to sort of rationalize this, you may want to just draw the parallel, right, to what we saw before, right? When the alkene, say for example, attacks, right? Right, you're going to have the alkene come in here. And let me draw this. Should I put this right? Right? We can think about this in a couple different ways. Again, if you want to have the alkene directly attack the palladium and leave the chloride, you could, in principle, imagine that reaction. I'm trying to decide how I want to sort of show this to you guys. Because what the intermediate formally is, and this is why I'm sort of debating how to show this to you guys, is, in essence, this sort of 2 + 2 reaction. So in this way, it's perhaps a little bit more difficult to draw that parallel. In principle, what happens is the palladium will coordinate to that alkene, okay, and then add across that bond. Unfortunately, I can't draw the same parallel that I drew before. What you have is this sort of species here, okay? So if you just think about making that carbon-carbon bond, in this case, you sort of think about making that carbon-carbon bond first. Now, it's not to say that we couldn't attack the palladium first, but it's going to be a reversible process, right? So over time, what's going to happen is we're going to make that carbon-carbon bond. And then the final step in this reaction is going to be very similar to what we saw previously in terms of a reductive elimination. But the question here becomes, you know, if we do that reductive elimination, we're going to generate the carbon-halogen bond. And then you can imagine we do an elimination at that point. But in principle, what happens, and what really happens, is what we call beta hydride elimination. Okay? And so we rarely see hydrides, we never see the hydride serve as sort of a leaving group. But in this case, that's kind of what happens. It's not really leaving as a leaving group, it's that the palladium is pulling off that hydride. We're going to make our double bond, okay? And from a mechanistic standpoint, this is where the base can sort of come in. Okay, because we're still palladium-2. It's often said that the base is in there to bring the palladium back to palladium-0. And you can think about it from this step here, right? So if you have that base in there, you sort of pluck off that proton, the electrons will go into the palladium, and then you need your halogen. So again, if you want to think about it as an oxidative, or as a reductive elimination again, and then bases in there to protonate that, you can sort of think about that in that way as well. Again, we're not too concerned about the sort of minute details of it, but rather wrapping your head around how this can happen, okay? So again, first step is the same, reductive elimination, same as the palladium-catalyzed cross-coupling. The second reaction, we bring in our nucleophile. We make a carbon-carbon bond, right? At this step, once we've made the carbon-carbon bond, now we have palladium in good proximity to do what's called a beta hydride elimination, to generate our alkene. However, we're still palladium-2. You could do the reductive elimination at that step, if you're more comfortable doing that, or you can have the base directly deprotonate and generate that. And again, this, I believe, is generally the mechanism that is invoked, the base actually mediating the elimination process, but I think you can rationalize the importance of it just based upon the fact that you're generating that acid as well. So either one, just to remember what's sort of in the reaction. Okay, so this is the second palladium-catalyzed process. It's called Heck reaction. And again, this reaction, as you can imagine, is really valuable, and one of the areas where this has had a huge, immense value has been in like medchem studies, right? You can imagine, we were talking about before about having a whole bunch of alkyl tin species, having a whole bunch of some alkyl iodide intermediate, and you want to try to put a whole bunch of new aryl groups to optimize, say for example, the drug, right? To tune in, say for example, selectivity or so forth. And so if you have your alkyl tin molecule as your intermediate, and then you treat it with all these different alkyl halides to bring in different groups, you can imagine generating very big libraries very quickly. And so this has had these two reactions in particular, palladium-catalyzed cross-coupling, Suzuki-Stilles, as well as the Heck reaction, have actually made enormous and had enormous impacts on society. In fact, when I was actually here, when I just started off, it was just a few years ago, the Nobel Prize was awarded for these three processes, the Stille, the Heck, and the Suzuki. So, okay. All right, so let's discuss a couple others. I think there might just be two more. There's two more palladium-catalyzed processes. Now, as we learned previously, so this is a Sonogashira reaction. So much like the alkene, right, you can also do this chemistry with alkynes. Okay, the mechanism is a little bit different, but you can sort of make that relationship, right? If you have an alkyl metal, boron, tin, you can do a direct coupling. Alternatively, if you have an alkene, you can directly change that hydrogen group, taking it a step further. If you have an alkyne, you can also do this process. So that's at least a way to perhaps remember all of these processes. And so with an alkene, it's called a Heck reaction. In the case of an alkyne, right, the additional, extra basically just from sp2 to sp3, you can also do this cross-coupling reaction. Again, it's going to be palladium-catalyzed. In this instance, there's going to be one subtle difference to this process, and that's that to drive this reaction, what you actually need is an additional additive. So we're going to have base in here, just like before. But what we're also going to have, and what we're going to need to do this reaction, is copper, and specifically copper 1. Okay, so there's sort of parallel here. Let's say copper X. And so as we'll see from a mechanistic standpoint, the copper, in much the same way, again, we've seen, how can we rationalize this? What's a better nucleophile, an alkene or an alkyne? Why? Well, I'm saying, yes. So if you can deprotonate an alkyne, yes. But just inherently speaking, if an alkyne were going to react, well, what's leaving behind? One is leaving behind a positive charge on an sp2 carbon. The other is leaving behind sp. So an alkene is going to be more reactive. And so it turns out that if you do these together, they're not going to work in the same way. You can't simply run the Heck reaction conditions with an alkyne. And what you need to add is this additional copper source, which becomes a nucleophile much in the way that perhaps you're thinking. Okay, and in this process, what you can do is you can make carbon-carbon bonds. And again, the mechanism is going to be similar again, right? So in the same way, right, if we have palladium 0, again, the same first step. Palladium 2. We're going to have that alkyl source. But again, in this case, what happens is you can't simply take this molecule and treat it with the alkyne. It will not add into this. But what it turns out, and this is, I can show you guys maybe one more reaction that's been on my mind lately. It sort of goes through a similar process. But as it turns out, if you take sort of copper 1, and you treat copper 1 with alkynes, what will happen is you will get to what's called a copper acetylide. Okay? So right, so it's called a copper acetylide. Okay, and so now we have a sort of a nucleophilic cuprate reagent. Again, still copper 1 in principle, right? Now that we've got that better nucleophilic character to it, now it can actually displace the bromide. If you want to think about it that way. And we'll discuss how that makes that in a second. I just want to complete this mechanism. Okay. You make your alkyne bond, right? And regenerate palladium-2. So the key here is that what the copper allows, right, is the formation, from a mechanistic standpoint, it's less, even though it's sort of, you may relate it in terms of the Heck, is in terms of, oh, you can do this with an alkene, can you also do this with an alkyne? But from a mechanistic standpoint, perhaps it's much better to sort of relate it to, say, for example, the Suzuki or Stille. But the question then becomes, how do you generate this copper acetylide? And these copper acetylides are actually really valuable for a variety of different reasons. Well, what happens in this reaction, again, we're going to have base in here as well, right? In this process here, right, you're going to generate copper bromide. And again, if copper bromide is our reagent, right, then you can see that it can also be catalytic in copper as well. Except that what's going to happen here, right, is that when we do this reaction, right? If you take this molecule and you treat it with copper in the presence of base, what's going to happen is the copper is actually going to coordinate to the alkyne. I've never been fully comfortable with this reaction. But at least in terms of drawing this, the copper coordinates. I like to think about it, even if it's not exactly like this, that once it coordinates, we're now making that carbon-hydrogen bond much more acidic, right? We can think about this as being a sort of a pi-Lewis acid, if you will, coordinating, making it more acidic. And then what happens is that base that we used previously now can actually deprotonate right, and generate the copper alkyne bond. You guys see that? So if we coordinate, right, you got the copper coordinated there. Once you deprotonate, then those electrons can go ahead and make a copper carbon bond, leaving the bromide. Okay, so during this process, now you have the base in there that's going to sequester this stuff. You have copper bromide. When you react this, when you react these two together, what do you generate? More copper bromide. So again, there's the overall process. The base is effectively there to again help sort of drive this bond. Okay? So there's the Sonic-Ashiro reaction. Mechanistically similar, I think, in many ways to the Suzuki instability. Questions? You guys look like you got questions. Questions? Yeah, so this is called a pi bond. This is organometallic chemistry. It's a copper pi bond. So it's organometallic chemistry. So what's that? Oh yeah. So it's a ligand. Okay, so the alkyne is effectively just serving as a ligand through the pi bonds. So the pi bonds are effectively donating their electron density into the copper as a ligand. So they're called, if you want to look into it, it's called like pi, you could call it like pi-Lewis acids or pi bonding metals or something like that. So again, we haven't really seen this before, so that's probably why you guys are like, whoa, what's going on here? But the copper, we haven't really discussed transition metal chemistry that much. What's happening here is the alkynes can actually serve as ligands, pi ligands, bind to the copper. You can think about that as being a Lewis acid activating process, right, whereby those are effectively pulling electron density out of here, which then allows the deprotonation. So it's not binding to either carbon; it's actually coordinating to the pi bond. So it's, yeah, we haven't really seen this that much. Okay, so anyway, that. The last reaction that we'll discuss that involves palladium-catalyzed cross-coupling, I think it's a little less interesting than some of these others, but there are things that are worth sort of mentioning. So we discussed alkenes with the Heck, we discussed alkynes with Sonic-Ashiro, again, metals of the two in terms of Stille and Suzuki. And it turns out that inserting into, so allylic alkylations, is a little bit different because we're not necessarily going to be talking about carbon-carbon bond-forming reactions, but this is more just palladium-catalyzed processes. And I'll show you a kind of a cool, I think one of my favorite examples of allylic alkylation after I sort of show you guys this. So, an allyl group, who knows what an allyl group is? Right? We probably said it, but maybe, right? This group here is called an allyl group. So when you have CH2 in an alkene, this is called an allyl group. So alkyl bromide is basically 3 carbons alkene and a bromide. Allyl alcohol, you might imagine, same thing, but an OH over here. Allyl Grignards, for example, are allyl groups with a Grignard over there. So this is an allyl group. We've probably seen it. I might have mentioned the term allyl. So we're all on the same page here. This is, when we're referring to allyl groups, what we're talking to is a carbon, sp hybridized carbon, or sorry, sp3 hybridized carbon adjacent to an alkene. Okay? And as it turns out that when you have a group like this, and we've seen this in the past a bit, right? That things like there's certain factors, whether it's acylic or allylic, there is this sort of perhaps ability of interesting chemistry to take place here, where, say, for example, if that was a carbocation, right, you'd have a resonance form, right? If that was an anion, you'd have a resonance form where the anion is on the other place, in the other face. So having this alkene at that position allows for some fairly interesting chemistry. But in the realm of palladium-catalyzed cross-coupling chemistry, we were talking about ligands, and we were just talking about pi bond ligands. One example of another class of ligands are allyl ligands. Okay, and so if you can imagine, if you could be in a situation where, say, for example, that was an anion, right? This is sort of what we were just discussing. You have this negative charge on one side, right? There's a negative charge on the other side. Sorry, there's an alkene on the other side, so you can resonate back and forth. And so you can sort of think about this, right, as that electron density being shared between those sort of two carbons, right? And so sometimes we'll draw it like this. This sort of dotted bond can be flowing through those two, just as sort of general, broad recognition of these sort of allyl groups. Now, you could also imagine the same thing, say, for example, from cations as well, and do the same thing. So why do we care? Well, in terms of palladium-catalyzed cross-coupling reactions, it turns out that palladium will insert into allyl, say, for example, acetates, I think is the classic example, right? So if you have, say, for example, an allyl acetate, or an allyl halide, or anything like this, palladium can, in fact, insert into this bond. Okay. When you insert into that bond, right, what you end up getting is, again, not completed insertion. What you can get to is a species like this. But furthermore, going back to things that we've never seen before that now we're going to see for the first time, again, whether you think about this as a cation or you think about it as an anion, you can sort of recognize that that palladium bond is a little bit different than your standard covalent bond, right? And what can happen is this palladium could, in fact, resonate to either, basically migrate from one side to the other. And in fact, doesn't really serve as either or, and so sometimes when we draw this, you sort of have this palladium-allyl complex. Okay, so the palladium is sort of bonded to both simultaneously, and so you get to sort of a species like this. Now, when you look at this molecule, what you may sort of recognize is, again, I showed this over here as a negative charge. But now that we've sort of coordinated, and we've got this sort of palladium-2 coordinated to it, in many ways, you can imagine chemistry taking place that effectively treats this as a pretty good electrophile, right? So we can imagine a mechanism in principle, and perhaps best drawn from this, although as we'll discuss in a moment, it can go from either face. We can imagine as sort of an nucleophilic addition into this compound. It's going to regenerate palladium-1, right? And so this adds in. generate palladium-0. Right? And in this case, again, depending upon what the base is, you've got the bromide counterion that can end up undergoing chemistry. So from a catalysis standpoint, unlike the alkyl halides that we had in the past, I'm going to show you a catalytic cycle. It sort of involves this interesting chemistry, right? And that's that if you have palladium-0, okay, what can happen is the palladium-0 can insert into an allyl leaving group. Oops, sorry, I put a bromide there. Okay, but in principle, it could be a leaving group, it could be a halogen. The point is that it's something you can insert into. Certainly, acetates are a little bit more stable, so you can see the advantages of something like an acetate, right? The double bond right there. Okay. Right, we insert in. Now, notice at this point, what can happen is that palladium can go back and forth between either side. So I'm recognize that it looks something like this, but in principle, in this case, it doesn't really matter, but right. But in principle, it can go back and forth between those two. Again, it's molecule symmetric, right? And then depending on which side you are, then the nucleophile could come in. Depending upon what the nucleophile is, they can either add in the way that I showed you guys here, or perhaps you can even have it attack directly. But again, the point is, nucleophile right? So the nucleophile, again, what's the counterion of the nucleophile? Well, I'll say, in this case, what we'll have is X minus, and again, if this is, say, for example, nucleophile M plus, and the salt will be M plus, and we'll sort of generate this process. Yeah? So that's what we're going to talk about in a second. Yes, so the question then becomes, in this case, it's symmetric, so it doesn't matter. How might we decide and how might we predict which way it would go? As you might imagine, people have probably worked out chemistry for it to go one way or the other. For the sake of this course, I think we could ask the question, though, or sort of rationalize it, especially in the final 2 minutes. If you did have substitution, so let's say, for example, if you had this here, right, then what we're dealing with is that compound here, and so the product that we're generating could be one of those two species, right? So the methyl group could be one place or the other. Now, what might be some factors, just to do a thought experiment, what might be some factors, again, depending upon whether it's allylic or not, what might be some of the factors that would lead to this one, right? This would be, yeah. Yes, this would be, say, for example, thermodynamic control. This one, on the other hand, again, if you have, say, for example, a nucleophile that would add 1,4, right, or 1,4 here or here, right, you can imagine if this is the more stable species just in solution and there's more of this around, then you want to add 1,4, then maybe you get the other one. So, but I would say, you know, for the sake of this course, I would just sort of assume thermodynamic control. How do you add in that some nucleophile? So we'll discuss, because we're completely out of time right now. What we'll discuss next week, I'll give some. We'll start with this next week, because your question is, what's the nucleophile, right?
No, over there, right? How do you get a nucleophile? No, down there.
1, 2, 3. Oh, I was saying if it was symmetric. Yeah. So I just threw it in there to sort of symmetrize. So we'll do specific examples of this class on Wednesday.